a single element. Okay? So what is its span? So what is the span of this single element? So I start off, say, what is the span of this is a vector space. The space which contains V0 and what else? All possible finite linear combinations, right? What are the combinations with one vector? Only the scalar multiples, right? The span of, by the views of rotation, I write it like this. This is nothing else but lambda V0. Right? So that's the. Oh, sorry. So, even if we had 0 here, this is my span of okay. Now it could be that this is it. This is all of, there is nothing else in V. Let's get an example. Take the reals as a vector space. Okay? Take any real number which is non-zero. Okay? Can you? Oof, 1 minute. Close this. If I take a non-zero real number, then span of X one minute. Hello? I'm class. class. মানে আমার মানে 6টার সময় হ্যাঁ 6:30 আসবেন So this is whole lot, right? Why? Take any real number. Take, well, already in span of X, 0 is there, so you need not think about 0, right? Take any real number Y. Non-zero. Now, why do I need this? Any real number is actually, because you have taken X to be non-zero. This is actually it's a multiple of X. As simple as this. Okay? So, the span of X is R. So, there can be vector spaces V where this procedure stops. Okay? But there are vector spaces R2, for instance. Okay? Let's take 1, 0. And the span this is exactly your x-axis. And definitely you know that this is not all of it. Right? You have the 0, 1 in the y-axis, which is not there. Okay? So, why I said so? So there can be cases where you might have a member here. You might have a member here. Okay? So I can have my next set, say S1, which is V0, V1. I can look into span of S1. What is it? It is all possible linear combinations of V0 and V1 along with 0, obviously. Okay? Alright? Okay. And I come up with again, there are vector spaces where this might stop. For instance, R2. It's exactly same that it stops there. Right? It stops there. So the question, and there are vector spaces, for instance, R3, if I take, so you see there is a pattern, right? If I take R3, then there is still another point here, right? Okay, before I move any further, observe something. The visible stages, it seems, the visible stages are these, in vector spaces, are these big blocks, subspaces. You might start off with this, okay? But it seems that you come up with a block that is visible as a subspace. The next block, okay, is not this plus a few things from here, but the second level of spanning. Yeah? So you can only see in grades, blocks, in vector spaces, unlike points or sets where you can add 1 or 2 points, right? So here you can add big chunks, you add vector spaces, right? Yeah? Okay. Try to keep this picture in mind. So the whole point that I am trying to make over here is there can be, so I can produce examples where for each natural number n, this procedure will stop. Okay? So there are cases like this for each n. There is a vector space V, V0, such that case, I'll do it with the Rn exactly. Okay? So R1 you saw 1, R2 you saw 2, R3 you will see 1 0 0 0 1 0 0 0 1, and so that's the trick that I'll do. Okay? That's the trick by which I'll construct. And there are cases when this never is true. That means for each n, or there exists a vector space such that for each let's have some examples for this. The prime example for this is this. Remember, these are all polynomials. Okay? And remember what was a polynomial? Polynomial right? It's an nth degree polynomial. So this is exactly in the span of obviously no. For each n there is a n plus, so there is a higher degree polynomial, right? So this you can have as many big chains as possible, but it still doesn't exhaust. Okay? Mode in fact, well, this is so. And then you know that all those things that we saw in that chain above, the infinitely many times differentiable functions on reals, 2 times differentiable, 3 times differentiable, 1 times continuous, all of them are like this. Right? Okay. So, the notion of a span brings us here. And so, distinctively, these are 2 different kinds of vector spaces. Okay? I'm almost done with today's time. So this brings us actually to the notion of finite dimensionality and infinite dimensionality. Okay? But to do that, I need to do 2 more things. The first thing is, suppose I tell you that I have a choice. I have a choice of vectors here. I have a choice of vectors here in this particular vector space where I stop at the, where I stop at the 3rd level. Okay? I tell you. The first question is it very specific about a point? That means if I start with V0 Is it true that I can select some other paths by which I can go, not the third level, but the fourth level? Yeah? So, I am saying, is it possible that I can choose another set of points over here such that these four, the span of it is, okay? Well, I'll show you, and these four, I mean to say that this one is not in this span, this one is not in the span of these two, and this one is in that way, in which I did. I will show that no. If in a vector space you start off and stop at a stage with one selection, you do so with every other selection. Okay? So what does this tell you? Does this not tell you that stopping at a stage is independent of the choice of how I start, right? However I know I start in this way, however I do so, I'll always stop at the 20th stage. If you told me that I stop at 20th stage, then however I start, I'll always stop at the 20th stage. Right? So it is so therefore stopping at the 20th stage is nothing to do with the point with which I start, so it's a property of that vector space itself. Okay? And so stopping at a stage, at a finite stage, I'll first establish that stopping at a finite stage is an intrinsic property of the vector space itself. So wherever you start off with, you never, if you stop at an nth stage for a vector space, wherever you start off with, you'll always stop at the nth stage. Okay? This number n is called the dimension of that vector space. Okay? And vector spaces for which you cannot find this stopping number, so however big you might go on, you still have some. They are called infinite dimensional spaces. Okay? So polynomials, for instance, is the vector space of all polynomials is infinite dimensional. The vector space of continuous functions, so real life, infinite dimensional. Okay, so there are several vector spaces which are infinite dimensional. Only a few. And so polynomials of degree at most n is finite dimensional. Okay? So that's the picture that we are trying to get towards. Okay? So next week, that means on Thursday, we will come to this. We will finally come to show that these are what is infinite dimensional. And there is a lot of work here. Although most of our course, we will be sticking to finite dimensional vector spaces only. But occasionally we will make statements which also holds for infinite, that is for all vector spaces. We will see that our results get much more sharper with finite dimensionals. Yeah? So with that, I'll stop here today. And yeah. Yes.
Hi.
Yes.
So sorry, I really do not mean to disturb the conversation. We just want to know in case times we're going to be doing a tutorial so that we can see how we can use all the information that was given to us and apply it.
Yes, you can.
Okay.
Proceed with your question.
No, I just need to know, Prof, do you have questions with you, or did you post them on my UNISA?
It's your questions. They are already given to you in self-assessments, in assignments. So, up to this point, what I have done, you can ask questions.
Okay, and then can we also, so if we leave now and we ask you questions via email, would you respond?
I think I respond immediately with emails.
Okay, alright, then that's fine. Thank you so much.
Thank you. Yeah. So,
sorry?
Yes?
Okay, I'm here from the Sunnyside campus, sir.
Yes.
I followed you from the day you started. I just have a request. After you explain like your proofs, for example, now you did the span and whatever we did today. Can you also go through an example with these things, putting figures into it, numbers, not just the mu's and the lambdas, so that we can have a feel of how this thing is applied?
Okay, firstly we must try to understand that proofs are themselves, the numbers are much more, numbers or such things are much more complicated. We will be using these propositions, these properties in application. We'll never be applying numbers to these proofs. So we will be applying this to examples. So for instance, you give me a problem about span. So I computed the span of a few things over here. Where is it? Here. So I was computing the span of X is R. The span of 1, 0 is this. I left it to you to compute the span of 1, 0 and 0, 1 is R2. Okay?
Yeah.
So this is where you are going to use the definition in applications, but proofs, they don't come any simpler than this, what you are seeing, because putting them in special cases doesn't make a proof simple.
Okay.
It makes it much more complicated.
Self-assessment questions that you posted, additional equals.
Somebody else talking.
Someone.
No, what I'm actually speaking about, I know you said that you can't change the prescribed textbook, but you recommend the textbook. They also display the proofs, and then they use examples of the application thereof. And it's more, I grasp it quicker in the book. Terminology used, what you are using, maybe I'm not familiar with it. That's the other part. So it makes it difficult to comprehend.
Yes, if you follow what I am doing from the first day, you should get up with the terminology by this time. So,
understand what you mean, but when I have to apply.
who's talking outside?
No, okay. Just a request.
Yeah.
No, I say what I asked was just a request.
No. You just give an example, then we can look into it.
Teaching math.
Okay. I'll have one when we start. on the next lesson, sir.
Okay.
Thank you.
Thank you.
That's an interesting
I think the parocenter, it's you're talking amidst yourselves, and it's being heard from here.
Oh, but I thought it was off. We're not even touching the button or anything.
Yeah. So, any further questions? So, I would actually suggest that in these tutorials, you come prepared with questions from what I have already taught. Otherwise, it shouldn't be okay, I'm developing a new thing every week, but it has been developed already, right? So you get prepared with this, and you come prepared with questions. That's the more important part of this interaction, which is questions from your side. And obviously you can post questions to me. I respond to it immediately almost. That's another issue, but you should come prepared with problems.
In the textbook, there are no proofs, they're just examples.
There is this other textbook which I referred to, Axler.
The name of the textbook?
I referred to that. There is also a link to it on the additional resources and in the tutorial letter. Axler is the author. The only difference with this approach and mine is he has considered scalars to be complex numbers, and I am considering them to be real numbers. Until and unless you come to eigenvalues and eigenvectors, at that point these two approaches really start differing. But up to that point, you don't need you just need the fact that with your scalars you can operate just like numbers. So you can add them, subtract them, multiply them, divide by non-zero ones and so on. Nothing else is required. Okay? The moment we come to complex numbers, there are some niceties about complex numbers which affect the property of vector spaces starting from eigenvalues, but not before that. In fact, even, I'm just tempted, but even much more, you may not even divide, and much of it will still work through. Much of this will still work through. Where it stops is, you cannot speak anymore about dimension. Okay? So that's where it stops. But if you can add, subtract, and multiply, not possibly divide always, then you can do all that we are doing, but dimension place is going to be different. Okay? So this is another nice book which you can follow. If you look into it. And there is a link to his website where he also has video lectures, but the video lectures refer to his chapters. And you can also listen to them, obviously. And this is an e-book in UNISA library, and the link to that is given in your tutorial letters. So, if you have the tutorial letter as a PDF, click over there, it will take you to this e-book site. Being an UNISA, you can always access it and download it. So, there is but you will be wasting time if you are just coming here without interacting on your side. It's more. See, the problem is with mathematics. It's very simple, but you have to do it. I don't. Why do I say it's a problem? It's not a problem at all. It's true everywhere. You cannot swim without swimming yourself. So you have to do it yourself.
And there's another lecture on Thursday.
Thursday.
Please.
Yes, sir. So in March, it will be Tuesdays and Thursdays.
Hello.
Yes.
Sorry, sir. What time is the lecture on Thursday?
3 to 6.
3 to 6 again.
Yes.
And then on what topics will we be discussing?
It will be about dimension, linear dependence, and independence.
Okay. Thank you so much.
Okay, any further questions? From any center? If not, then let us disperse.